Okay. Hi, my name is Sasha Fedorova, and I'm going to talk briefly about what I do in general and for Cohesa specifically. And so let me share the screen to show a few slides. It's going to take a couple of seconds. There we go. So how do I move that away? Okay, so I did my PhD at Harvard, and during the same time, I was a perpetual intern at Sun Microsystems Labs, where I worked on transactional memory, OS scheduling, and I took part in writing the first Niagara hardware simulator. Then after that, I joined SFU. I was assistant and associate professor there. And then I joined UBC 2 years ago as an associate professor. And at the same time, I also do consulting for MongoDB, in particular for their Wired Tiger storage team. It's a key value store that's on the back end of Mongo. And yeah, that's a great gig because I get to write real code every Wednesday. Now, my research focuses on systems. So what does system software mean? So, I mean, there are applications and there's hardware, so that's clear. And system software sort of sits in between. And its job, well, one of its jobs is to basically make the life of applications easier so that applications don't have to cater directly to every new piece of hardware that comes out, and so that application writers can focus on functionality and not on things like, you know, performance, energy efficiency, and hopefully system software can take care of all of that so that applications run efficiently without developers thinking about that. That's, of course, the ideal situation. We're not there yet. So there's a lot of interesting research topics in that realm. Here's a few example projects that I've done. Perhaps the biggest one that spanned probably 10 years and many different projects in that area is we used OS Thread Scheduler to optimize how applications use various shared resources on multi-core hardware. So caches, memory bandwidth. Turns out that the thread scheduler was a very good hammer because how you assign threads to cores actually determines how you share the resources. So there was a lot of interesting things to learn in that respect. Then we have a project on log-free synchronization. And my recent passion is performance comprehension. So when I work for Wired Tiger, I solve a lot of performance issues. And so in the process of doing that, I realized that performance tools actually suck. And every time you have a new performance problem, that is non-trivial, you pretty much have to write a new performance tool. And so now I'm studying this problem in a more formal, researchy way, and I'm asking questions: how do software engineers debug performance, and how can we help them? So that's the background. Now, what am I actually doing for Cohesa under the umbrella of the Cohesa project? So this is going to be very broad and non-specific because we're just starting out. This is a pretty new area for me and my students. So we've been dabbling with running various models on GPUs, and it looks like the direction we're going to take has to do with training very large models. So there are some models that basically take a lot of space. And so the models themselves are large, and also the training data sets are very large, so that you can't, it's not practical to train the model on a single GPU host. especially because these hosts these days are limited in how much memory they have. You don't see GPUs with, you know, a couple of terabytes of RAM. And so what people do is they train the model on several hosts. So the most popular way to parallelize this type of training is to use data parallelism. And this has to do with the reasons that are connected to, you know, machine learning and algorithms and convergence and all of that. So basically, this is the preferred way to do things right now. I'm not saying it's the only way, but from what we know so far, this is how people do it. So basically, there are a few hosts, and every host has a copy of the model. And then the data set, the training data set is sharded between the hosts. And then what each host does is trains its own separate model. And the way you train the model is you do this multiple iterations, and, you know, in every iteration you do some training, and then you back propagate the coefficients, and so on and so forth. Now, the thing is, if you want to have an accurate model, a model that actually has a good predictive power, you have to exchange your training parameters with all the other hosts. Because if you train in isolation and then a day later you ask other hosts, hey, what parameters you have, then you're not going to get a good result. So you have to, the more often you exchange the parameters, the higher quality of the model you get. And this exchange of parameters is actually quite expensive on modern networks, because you have to do this pretty often, this exchange of parameters. And the amount of information that you have to send is very large. So you basically have to send the entire model, and models can reach hundreds of megabytes in size. And so if you have a few hosts, like 8 hosts that are training in parallel, and they're at each iteration, they're sending the parameters, they're distributing them, then they're collecting, they're sending their own parameters, they're collecting the parameters from everybody else. So it turns out that network is the bottleneck. And this is a bit less of a problem on hosts that are equipped with expensive, relatively more expensive network interfaces such as InfiniBand. This is more of a problem on, you know, more general purpose hosts like 10 gigabit Ethernet. And so the question that we're trying to ask is basically, you know, how can we make this better? Right now, we're at a very early stages of this research. We're just learning what has been done, and we're trying to get our setup going and reproduce some of the results that others have seen, just so that we can learn. And so I'm not ready yet to tell you about, you know, great ideas or accomplishments that we have in the space, because there's none. We're still learning what to do. So this completes the technical part of my presentation. And just to end with something totally non-related and personal, a couple of interesting things about me. I'm learning to dance ballet. I'm learning French, and I'm expecting my second daughter to arrive any day now. Okay, that's it. If you have any questions or suggestions, that would be great.
Yeah. So thank you, Sasha, and congratulations again. Anyone from remote has any questions for Sasha? Okay.
Actually, I do. So yeah, congratulations, Sasha, but and congratulations on doing this right at this point. But for your very large models, where are you getting them?
So there is a couple of models. Well, basically, the short answer is online.
Oh, okay.
So there was a couple of models that you can get, and we're using MXNet
Okay.
as our framework, and there is one speech recognition and speech synthesis model that we found. But basically, if you, I can connect you with the students and I'll give you, more details about exactly where they got them and how they set them up. So we're collaborating with Gena Pikimenko here at, well, not here, but there at U of T. And he's of great help to point us at some, real world models that people use. So yeah, if you're interested, we'll be very happy to share and chat about setting them up, because actually there's a lot of just effort and time goes into making sure that you're running the right thing and making sure that it's actually training. So, and his students have done this work, and my students have almost done this work already. So if you're just starting up, it's great to work with somebody who's done it, so you can save yourself that time.
All right, thanks.
We're happy to chat about that.
We are also, we don't have big networks, but we have a collection which we plan to release for the network engineers. They're all open stuff for planning. So, for example, we can sit down with Clark, all of us, and see whether we can do that a common repository where people can go grab models to the degree possible and continue the research. That's it's great you're doing this. We don't have any big models. We just find whatever we can. But we do have a collection. I don't know. It depends how many we have. Different types. And we'll be happy to share all of them. Okay, so do we have any other questions for Sasha? Nice. Okay, thanks a lot. Clark, maybe you can take the floor now and introduce yourself.
All right. Let me see how I do this. So we got the same learning curve, I guess.
We can definitely see you.
Okay, good. That shares the screen. All right, cool. So I did make this presentation. So you've seen me already, but anyway. So by the way, my voice does not sound like this normally. I've got the flu, and I've somehow managed to also get a little bit of laryngitis. So I'm sounding a bit prepubescent or something. I don't know. It doesn't seem to come out right. But anyway. Let me see. How do I display this thing? I'm not used to this Windows machine, so I guess just full screen mode. All right, so I'm going to give a bit of background. I'm also in the same level as Sasha there. So I do some compiler program analysis and optimization, and I'm going to tell you just a little bit about what I've been doing for a long time now, actually, a little bit on the thread level speculation. I've actually got another research area and domain I'm interested in, which is computer games, where I've been focusing on companion AI, which doesn't have a lot to do with Cohesa, I guess, but on the other hand, maybe there is some overlap in the AI things. Game AI is a bit different from formal AI, though. And at the end, I'm going to just mention a few of the Cohesa-related directions that I've started looking at. So compiler analysis and optimization. I've started looking at some of the past stuff I've done, and it's kind of dense as all over the place, actually. But some low-level things and some high-level things. So some range analysis, trying to predict the behavior or analyze the behavior of variables, profiling metrics, some lower-level analysis of programs, the iCache, and looking for phases of computation to try and take advantage of that. Visualization. Also some things to do with concurrent programs, so some automatic locking, which I saw Sasha also started to work on as well. May happen in parallel analysis, which was supposed to be a general analysis for concurrent programs, and a bit of stuff to do more specifically with virtual machines, some code copying stuff and some specialization. I'm going to try and show you or tell you about something that I think is kind of interesting and sort of cherry pick a few fun ideas from stuff I've done, I guess. So the idea here of thread level speculation, which is somewhat related to transactional programming. It's a runtime optimization for sequential programs. It's actually a form of automatic parallelization. And the idea is that we have a sequential program and we'd like to take advantage of it and make use of the cores that we have in a multi-core system that are otherwise sitting idle. So get parallel performance without actually doing the parallelization in a nice safety kind of safe kind of way. And the idea of this, I'm going to give a bit more detail on this, I guess, than you might have seen otherwise. The idea is that we're going to spawn threads to execute in the future. We do this at a fork point, and they start executing from the join point. So the fork to join code and the join to execute and the join onward code execute in parallel. A bit easier to see as a picture. So down the screen here, we have our normal execution flow, non-speculative thread on the left here. And we might choose at a certain point to fork a thread that's going to start executing in the future at this join point. And that we make our other cores execute, and thus we get parallelism out of it. You notice I drew them a bit offset because there's a bit of overhead involved in this, as you might imagine. And it's overhead in terms of the mechanics of starting threads and so forth, but also overhead in the sense of trying to make sure that everything actually works and stays as and produces a sequential execution in the end. Because in the speculative code, we're not sure of the actual program state it's executing in the future. We're not even really sure of the control flow, or frankly, in the worst case, if even whether we'll even get there. So we have to do a lot of tricks to try and make this work. And there's two main features that come out of this, or two main things we use. So one, in our speculative code, we're going to have a write buffer, which tries to make sure that everything we do in the speculative code doesn't impact the main thread, main execution. We also have a read buffer that tries to track the state in which we started off in, so that when our thread gets to our main non-speculative thread gets to the join point, we can actually validate whether the actual state and the assumed state of the speculative thread are indeed the same thing, so that we know we actually got the correct execution. So we have this whole validate and commit process where we try and look at the read buffer, make sure it matches the actual state, and if so, we can grab this write buffer and put it in the main memory. And the neat idea in this is that it's safe. If we find out this read buffer isn't part of our actual state, we can just throw the whole thing away. So as I mentioned, overhead concerns, lots of things we're doing inside here. We have to make sure the benefit outweighs the cost, and we have to make sure that we actually do get some speed up out of it. We have to speculate in the right places that are going to work, and there's a lot of work that ends up going inside there. The interesting part here is that it turned into a lot of different design variations and trying to look at different systems that have done this. This idea has been around since the 1990s, and people have produced all sorts of different systems for doing this, but trying to compare them has been kind of the hard part. So the work we've been doing in my lab has been mainly focused on a pure software approach. So most of the TLS designs actually used hardware techniques. And we built two systems to do this so far, at least. One based on Java using method level speculation. I'll talk a bit about some of the ideas inside there. And one that was based on LLVM, which could do a lot more and actually got a lot further in this and encountered some neat hardware limitations as well. So the Java version, in this system, this was done by Chris Pickett, one of my former PhD students. It's a method level approach. And to know what that is, I have to show you what these different speculative models actually are. So loop level speculation is a common way of doing things. Here we might say that we have a loop and we fork a new thread at the beginning of an iteration, and a join point, the point at which the speculation starts, is the end of that iteration or the start of the next iteration. And then we get multiple iterations in parallel. Ideally, we do this for more and so forth inside there. Method level speculation, we fork a new thread at a call site and it starts executing the continuation while we execute the body. Right? So we get the continuation and the body in parallel. And the interesting feature that brings out is that the continuation of a method often involves doing something with that return value. So we need to know what that return value is if we're going to be able to make it actually go. So we have to be able to guess this. And it brings in this kind of cool problem of return value prediction. And in fact, there's lots of predictors people use for this kind of thing. They try and look at the return value and try and guess at what the return value will be the next time we come around to that same function. So there's last value predictors. Some of this is stuff I think is done routinely in a hardware context in terms of value prediction. But we have last value predictors where we just say that the last thing we saw there is going to be the same as the next thing we see there. Stride predictors look for a constant difference between return values. So if I see a pattern of 1, 2, 3, 4, I'm going to predict 5. And we can get into more complex ones that start to look at more history. So 2 delta only updates the last value if it sees the same thing twice in a row. Finite context looks for patterns. If I see N, then M, then P, then Q, and then N, I'm going to guess an M. And even more complex and more memory intensive is this idea of a memorization predictor, where I say that there's an input-output mapping, and I keep track of that. So if I've seen input 1 and that produced output 1, and then input 2 and produced output 2, if I see input 2 again, I'm going to guess output 2. Obviously, there's cost-benefit trade-off inside these things. And unfortunately, we can't just say one predictor is best in all cases, because different functions have a nicer, act better with different predictors. So we built a hybrid predictor out of this, which runs all the predictors at once, sort of a limit study, I guess, to see how well we can do. And the idea was that we would run them all at once. Once we reached a certain confidence level, we might specialize this and reduce it to a single predictor to reduce the overhead of running all the predictors at once. And of course, we could despecialize and respecialize later on. And the thing I thought was interesting and cool about this was the level of accuracy we could actually get out of it. And sorry about the grainy pictures here, but these are taken from a paper. So this is the accuracy level over here, and these are some Java programs. And you don't have to worry about the flavors of it. Online is the one that was probably most realistic. But we can get anywhere, from about slightly under 40% to over 80% accurate in predicting the return values of functions, which I thought was surprising. Most of your programs you don't need to write, you can just predict them, right? Or don't need to execute. It just did come, of course, with a major slowdown. It's one of the limitations of our Java version, that we never really did get decent speed up out of it. But one of the things we did learn inside there is that there's a lot of different ways we can do speculation. When we tried to look at how other people were doing things, realized there's some fundamental differences in how people address this. And one of those ways was thinking about how we allocate threads inside here. Can different speculations, or can we have more than one speculative thread? Can one thread launch multiple speculations? Can speculative threads have their own speculative children, and so forth? Nested speculation inside here. And it sort of is interesting because one of the reasons we identified for varying performance in this case was the fact that there's these funny dependencies that show up when we try and look at speculation. If I have one extra idle core, and I encounter a method called foo, and I decide to speculate on that, and so the continuation starts executing in parallel as I go inside the body, I'm trading off the opportunity to actually do speculation inside the method at a different method call. So inside here, we're basically guessing whether parallelizing foo and bar over here is better than parallelizing these two inner function calls. So that ends up being kind of a hard thing to optimize for. The other speculation system we did was MUTLS, which is an LLVM-based implementation. So we had any source or target. Mainly we looked at C and Fortran and Intel AMD inside there. And it was a bit more flexible. It could speculate anywhere, but we did focus on a bit more loop-based things. And for there, we actually did a real speed up. I'll show you a picture at the end on non-trivial benchmarks and workloads. But it was awfully complex, and there's a lot of interesting design tuning that showed up inside there. And one of the sort of interesting ideas that came out of that one was this limitation. And since you're talking about memory issues in the system, the memory machine learning stuff, there's some correspondence inside here. We're hitting limits in terms of how we transfer large chunks of memory around. So the coarse parallelism we get out of thread level speculation, software-based approaches, implies these validation commit buffers get really, really big. And then we're shoveling around large chunks of memory. And if you think about what happens, I'll skip this slide, but this is the basic idea that we had for this, right? Is that we have main memory, we have a non-speculative thread that's reading and writing the main memory, and then our speculative threads all have these read and write buffers. And these are the buffers that get very, very big. When we validate things, we have to traverse this entire read buffer, and then to actually commit it, we have to flush this entire write buffer into main memory. And these things can get into many megabytes. So the idea of version control in this case is something we might call a lazy scheme. We could try and improve that. We did look at some parallelization of it, where we try and do the validation commit in parallel using extra cores that were otherwise idle as well anyway, and also some vectorization. But it sort of came about that maybe this is not really the best way to do it. And if we thought about how this is working, the way we set this up is that throwing away a thread is very cheap, because if we decide that it doesn't validate, then we just throw away the whole buffer. It doesn't cost us anything extra after that. But the actual commit part and the validation itself is very, very expensive. We're traversing these big buffers. And hopefully we're expecting that our speculation should succeed so that we actually do get some performance out of this. We're trying to avoid misspeculation. So it'd actually be better the other way around, that if we made the thread discarding the abort part inside here very expensive, but the validation commit was super cheap, then we might do a little bit better. And this is an approach that's been done by a few other people, and we built it into our own system, MUTLS. The idea here is that our threads write to main memory directly, and therefore there's no actual commit overhead. I'll show a picture, it's a bit easy to understand. So here we have a whole bunch of speculative threads. We don't have a non-speculative thread anymore. They're all writing into main memory, but they're keeping track of what they do so that they can undo it. We keep track of also the order of the threads, so we know which thread is more speculative than which thread. So we do have an oldest speculative thread, which is essentially our non-speculative. And then we have a version tracking system. So every time we touch a variable, reading and writing, we have to go check which version we're actually reading or writing and decide whether we're reading and writing something that's from the future that might be bad, or something from the past that might be okay, and undo things accordingly. So the advantage of that is that there's no commit phase, so the commit is zero cost. But the drawbacks is that we have to put these version checks, and then we have more errors inside here, and the rollback's a lot more complicated. And we don't get a progress guarantee as we do out of the lazy version, or at least not as nice of one. Our version inside MUTLS actually did both of these. So we had an eager version and then a fallback to a lazy. Here's some performance numbers, so you can see that these are all little tiny figures. These are all benchmarks under here, and on the bottom row is the number of threads or number of cores we had up to from 1 to 64, and then on the left side is the speed up factor. And we get different speed ups in different cases. The graphs or the lines to look at would be the purple one is our lazy only version, and then the green one is our hybrid version, and the blue one is our eager only version. So the green one is the one we hope to, that's our hybrid form. And so we can see sometimes the lazy does better, sometimes the eager does better, but generally speaking, the hybrid tends to do fairly well, sometimes better, sometimes worse. The only one that didn't do very well on was FFT. So that was kind of nice. So there's the actual speed up. Now, something to keep in mind is that we're not trying to compete with hand parallelized systems. We don't expect to get good parallelism with respect to an optimal performance kind of system, but we're trying to get something that's basically free. We have idle cores, let's try and exploit them. So here 1.0 is the normalized version of an OpenMP manual version, and then here's our relative speed up. We actually did get better in one of them. The FFT, as it turns out, with certain configurations, but generally speaking, we don't do better, but at least we're not doing zero. We actually are getting speed up out of it. So that's just some of the background stuff to show the kinds of things I've been doing. For the Cohesa related things, I have a couple students working on this. We've been mainly focused on doing some setup for some basic profiling and trying to get a bunch of different systems together. So I wanted to have a look because I'm not really sure which one of these is best. So Theano is obviously the one that's got a bit more cachet with our group here, right? But PyTorch and TensorFlow are obviously candidates as well. And so here's where I was interested in the workflows. We've been using CFAR and MNIST. We wanted like to get a few others inside there. We have one that's custom for a game context that Jonathan did as well, that would be interesting to look at. But we don't have a lot of workloads. But we've been trying to do also some at the same time, some initial experiments, trying to look at the trade-offs with the precision, because we know that's an interesting idea. And so we were able to replicate some of that prior work the other guys have done, where we see that lowering precision in some layers at least gives you a good performance precision trade-off in the, or performance accuracy trade-off, this is what that should say actually. So we're going to try to look at a little bit more of that and see where we can actually reduce precision in to smaller number of bits, and with the expectation that there's going to be some, hopefully some magic hardware that can actually help us and make that indeed a worthwhile thing to do. So we've been looking at techniques for adjusting the precision and trying to do this in a more and more automatic and fine-grained kind of way. So we'd like to change precision layer by layer. We want to try and apply this in the training and testing phases, so we can see that works nicely in testing. We're trying to do a little bit of that in training, in the sense of also trying to get some dynamic adaptation so that it's not up to the user to try and do this. And again, like Sasha, I don't have any nice results to show you. Just a moment. We have a bunch of preliminary experiments, some of which worked, some of which seemed to not work, but it turned out there was a bug, and therefore we're trying them again, and so forth. But that's the direction we're headed in. So I think that's all I've got to show you. And that's how I stop sharing things. Right? So there we go. That's what I've been up to.
Thank you, Clark. Any questions for Clark at the moment?
I have a comment and a question. We're going to set up. We're in the process of setting up the website with the benchmarks that we have created. So I'll share that with you in case you want to either use something or contribute something, depending on where you are.
Okay, great, thanks.
And another question that I had, not related to Cohesa, so I'm just going to mention it quickly and then we should take it offline, is that I noticed that in your very first slide, you had a data structure visualization.
Yep.
Yeah, we're really interested in that for our performance analysis work, and we found this to be really, really hard.
Yes, so did we.
Yeah, so if you have anything, written or, just want to chat, that would be great.
Sure. I have one paper on that because yes, indeed, it turns out to be dramatically a much harder problem than we thought it would be. So I can show you that one paper. That's basically all we did on it, though, and that was a few years ago.
Yeah, that would be great. Thanks.
Okay.
Now, on the note of websites, we've been evaluating some options. The plan is within a month or so soon to have a website for the project overall and a wiki underneath where people are going to be able to. We're going to have a public area and a private area where people have to log in. We can use that to disseminate models. I'm not saying that you should pull in your stuff on that. I'm just saying we can put a link there. So there's a common repository where people can go and look at what everybody else is working on, and also if somebody wishes to put stuff there, there's going to be a lot of storage available. And then we do have the Slack online for collaboration. I mean, we've been using it on and off, but I think we can, as people are hiring people this year to staff the project, I think we're going to have a lot more opportunity to work together as we wish. So thank you both for taking the time today. I really appreciate it. Sasha, all the best. You get some sleep now if you can. You know this thing better than I do, I suppose. And we're going to have, there is an RPC meeting, the Research Program Committee meeting sometime in April. I suppose we're not going to expect you to participate in that. But we're going to have to work out some way to get some updates on what you're doing and what others are doing too. We should probably start off online on how we're going to handle that so that you can involve with that as much as you wish and as much as you can. So thank you all. The next, this seminar series is going to continue now. We're going to do every 2 weeks as planned. I'm going to reach out to some of you. If anybody wants to volunteer, please go ahead. But otherwise, I'm going to reach out to specific people and try to entice them to participate next time around. And we're going to see, hopefully later on, we can have, after we're done introducing ourselves to everybody else, we can have more specific let's read papers, let's see, review what everybody's doing at the technical side. It's going to take a while, we understand that, but I think it's a good start. So thank you all for being here today, and I will see you all in 2 weeks. Thank you.
Thank you.
Thank you. Bye.
Bye.
I guess this is saved, right? So.
Thanks for coming today. Maybe we should start posting this for people to